Good morning, ma'am. Myself D. Kasimule. I'm from Triple E Department. Today topic name is Q factor. Then go to the introduction to Q factor. The Q factor is dimensionless parameters used in various fields, including engineering and physics. It quantifies the performance of accelerators and resonators, especially in terms of the energy losses. A higher Q factor indicates lower energy loss relative to stored energy, which is desirable in many applications. Definition of Q factors. The Q factor is defined as the ratio of the resonant frequency to the bandwidth of the system. Mathematically, it can be expressed as a Q is equals to F naught divided by del F, where F naught is the resonant frequency and del F is the bandwidth. This definition highlights the efficiency of the oscillators in maintaining the oscillations over a narrow frequency range. This is basic Q factor graph. Importance of the Q factor. The Q factor is crucial in determining the selectivity and sensitivity of filters in the communication systems. It plays a significant role in the performance of a resonant circuits, affecting signals clarity and stability. In mechanical systems, a higher Q factor can lead to better performance in devices like gyroscopes and sensors. Applications in electronics. In electronics, Q factor is In electronics, the Q factor is used to evaluate the performance of inductors and capacitors in circuits. Q inductors are essential for the RF applications where signal integrity is paramount. The Q factor also influences the design of oscillators and phase lock loops in communication devices. Q factor in mechanical systems. In mechanical systems, the Q factor describes the energy dissipations characteristic of vibrating systems. System with a high Q factor can be oscillated with minimal damping, lead to enhanced performance. Example include turning forks and musical instruments where resonance is exploited for sound productions. Measuring Q factor. The Q factor can be measured using various methods, including the bandwidth method and the ring down the method. The bandwidth method involves determining the frequency range over which the system can be oscillate effectively. The ring down method measures how quickly an oscillation dies out, providing into the energy losses. Factor affecting Q factor. Several factors influence the Q factor, including material properties, geometric in electronic components, parasitics, resistance, and capacitance can lower the Q factor. In mechanical system, internal frictions and material dumping also play significant roles in Q factor reduction. Q factor in optical system. The Q factor is applicable in photonics, particularly in optical cavities and resonators. In this context, in describe how well light is confined within a cavity, impacting a laser performance. Higher Q factor in optical resonators lead to increased intensity and stability of laser output. Challenges and limitations. While a higher Q factor is often desirable, it can be lead to challenges such as increased sensitivity to environmental changes. System with extremely higher Q factor may be more prone to nonlinear effectors applicating their uses. Balancing Q factor with the other performance metrics is essential for the particle applications in engineering. Conclusion. The Q factor is visual concepts across various domains influencing the efficiency and performance of systems. Understanding the and optimizing the Q factor can lead to advancement in a technology and engineering design. As research continues, new method to enhance Q factor will drive innovation in may field. Feel free to modify or expand upon any these slides is needed. Thank you.